So our third speaker today is Dr. Maria Meledina, I hope, who's joining us from ThermoFisher Scientific. She is a product manager in charge of high-end TEM products at ThermoFisher, and she's come here to tell us about improving analytical STEM for quantum material characterization.
So, hi everyone. Thanks for arranging such a cool workshop. I am in fact myself rooting into material science, so my first degree is in material science. So I'm always feeling super excited to highlight actually the instrumental capabilities for the relevant materials. And in this talk, I combine together a lot of spectroscopy. So it's going to be a very colorful one. And I will show all the analytic stuff which you can do with our instruments. So this is, in short, let's say, an overview of our TM family. So we have Spectra, and just this summer, in August, we introduced the new baby, Iliad 300 and Iliad Ultra. So Spectra is quite famous and well established for the ease of use, thanks to Velox software, automation, it's heavily automated, alignment, processing, and so on. A resolution, basically we can get the best resolution and sensitivity. And with introducing Iliad, we also, let's say, ramp up the spectroscopy story by expanding analytical capabilities also into EELs. And we are pushing forward already the existing stuff which we have there for the dose optimization with the introduction of the nanopulsar. So I will start with saying a couple of words of HT flexibility, because with our Ultra instruments, basically with Spectra Ultra and Iliad Ultra, you can switch between different HTs in terms of minutes. But first of all, why would you actually need to do it? So first reasoning behind this is actually that different techniques in our microscopes require different conditions, right? So if you are doing imaging, you in general want to be at high HT to achieve the best resolution. If you are running EDX, you want to be in the medium range of HTs. EELs is a funny one, because for core loss, you usually want to stay at high HTs, and for low loss, for band gaps, plasmonics, or photonics, you usually want to go low to get into the best resolution. And the final parameter here actually is the sample itself, because different samples suffer from the different beam damage mechanisms, right? So when you want to fight against the knock-on damage for the 2D materials, let's say as molybdenum disulfide, you in general want to go to low HT. And here is just an example of molybdenum disulfide bilayer. And the IDPC image is taken at 30 keV, so super low HT, basically, that's like SEM range. If you want to fight against radiolysis, you usually want to go as far as possible, right? As high as possible. And here is an example of basically DSO, dysprosium scandate, perovskite. You can see dysprosium dumbbells very well. The image is taken at 300 keV. And this is really a nice example. It's not really a quantum material, but I decided to still include it. It's a zeolite. And the guys did in situ with it, actually with protochips holder, I think it was published. And they were running IDPC, as I told, at HT as high as possible, at 300 keV in this case, but with very low beam current, right? The dose is super low, and they published, I really love this paper in Science. So I think it's really a good showcase of why would you need to stay high for imaging the dose-sensitive materials, right? Going into a bit of detector sensitivity. So these are the data which is taken with our UltraX. And UltraX, just saying, holds the World Guinness records as the most sensitive EDX detector. And you can see, again, one of my favorite materials, dysprosium scandium oxide maps. And the data, by the way, was recorded by Chinem, who used to work here. So I think she would be happy if I mention it. And it's also taken at 300. The total dose for EDX is not too high, no filtering, so that's the raw imaging. And you can see the solid angle with UltraX is super high. So it's basically brilliant EDX. Here is a little movie. I cut it out from, we're also running a little YouTube channel with a lot of how-to movies, right? We are doing a bit more of explanation here, but here I just cut out the EDX live mapping. My colleague Rachel took it, and she basically just started EDX acquisition. We also have EDC electron dose control, but I'm mainly talking on spectroscopy, so I will not elaborate too much on it. So you can see in the bottom of the image, there was highlighted the dose, and the dose rate is also highlighted. So you see, I mean, she started EDX acquisition less than a minute ago. She went to processing window. She's identifying the elements which are there. It's basically also a very cool stack of perovskites. We got the sample from Jover back from EMAT. And this material was published actually in Nature. So barium titanate, strontium titanate, and LMO on top of each other. And you will see that in less than a couple of minutes, she will get brilliant atomic resolution maps there, right? So she's basically, while acquiring, she's doing processing, putting the elements on. You can also do filtering, right? She can apply some filtering. And you can see that you already, like in less than a couple of minutes, have super cool EDX for a very nice quantum material, right? I mean, she's very nice. Rachel is really nice in choosing pretty colors for elements. And you can see that the map looks really, really nice. Here I just cut out the, nice fancy moment. But in the YouTube channel, we really explain how to get into it, how to orient the sample, and so on and so on. One more movie, also taken actually by CHIDEM, where we combine the two ultra functionalities, HT switch and Ultra X. And she's also looking at a very pretty sample. And she took a first image at 300 keV, and then she's running an EDX map. It takes less than 15 minutes. And then she's taking, let's say, an image to check how the sample is doing. And you can see that basically at 300 HT, it gets damaged. She drilled a hole in it. So she's jumping into 200 HT, accelerating voltage, again taking a pretty good EDX map. And then she will take one more image, to see how the sample is doing. So I think that's actually the power of Ultra platform, right? When you can freely jump between the different HTs, and within 1 hour, you have the complete chemical characterization of your sample. So now let's go and look at the new baby. So Iliad, I'm very always touched because I was very plugged into that development. And Iliad is the new platform which we just launched this summer. On top of all the functionalities, it has several, let's say, latest and greatest modules. And it's heavily packed by all the patents. So some patents are already given, some patents are still pending. And what we're really proud about Iliad is that it's really very much applications inspired. So all the technology is translated into, applied work. So application speaking, the new model from top to bottom, below the gun we have the nanopulsar, and you can use it, for example, for dose optimization or for smart data collection strategies. The big one below is a filter. And basically, it's even hard to call it a filter because it's really deeply integrated with the column optics. It really matters. And it stands out with very high optic stability. And these two first, let's say, points which I mentioned give logical continuations in something which we are calling always in focus technology. I will comment on it a bit later. And together with it, we're introducing a couple of new modes. The first one is called multi-yields. And you can use it for collecting up to 5 energy ranges with, for example, high energy resolution. The second one is a pretty cool one. It's called X-yields, or extreme energy loss yields mode, for the collection of very high energy losses with yields. And actually, thanks to the stability and the integration of optics, and also thanks to the software integration, it's very easy to use. And you can also script whatever you want. If you want to do some kind of strange experiment, or if you want to optimize your usual workflows, you can do it using the AutoScript. So what can you actually do with it? I mean, I mentioned the nanopulsar. Nanopulsar is quite, and easy. It's electrostatic beam blanker. As I told you, can use it for the dose optimization, data collection, time-resolved experiments. And I've put here a couple of examples. I mean, we have more, but I just decided to take those that are relatively easy to follow. So here, basically, there is an example with ESBB inactive and ESBB active, meaning for the inactive one, we just basically throw in quite a lot of dose into the sample by having the flyback unblanked. And when we basically just activate the ESBB and blank the flyback, we already save a lot of dose which we do not throw onto the sample. What I also really like is the work which we did actually with DTU, with the group of Stig Helvig, when we were looking together at molybdenum disulfide using the pulsed and unpulsed mode. And we've found really cool stuff, basically, that it really matters for the dose mitigation. We are still in process of, let's say, analyzing and digesting it, and soon we'll submit for publications. Coming to the next model, which is actually the filter. The filter has quite a lot of really cool goodies in it. So first, the prism is large, helps to reduce the aberrations. The optics are hugely stable, as I told. The tuning is quite automated. Basically, we call it auto-tuning. And fast electrostatic optics, really helpful for multi-eels, and we have our own zebra detector. And here is actually a little illustration which I took from our life science colleagues, because they were measuring the stability of the filter for super long times. And you can see that's super stable. And the only bump you have here is when they are refilling the nitrogen. So I mentioned in the beginning the always in focus technology, which we have for, as the outcome of the deep integration. And here is an example of always in focus and multi-eels. So basically, in this case, we're having triple eels, right? We are looking at 3 windows. DSO, my favorite sample, low HT, highly zoomed in energy. And the top example is basically illustrating what you see as a usual operator, right? You typically come to the ZLP, focus on it, but then you go to the core losses, you start losing the energy resolution. Also, I tend to jump between the camera lens, actually to optimize the collection. And usually you want to be low, but you can see when you go to the low camera lens, you also lose the energy resolution. And when you go also further onto, let's say, higher energy onsets, you are again in trouble because dysprosium is basically looking like a hill. And if you apply the always in focus, which includes, we do several things with it, you get into much better data set. ZLP looks pretty much the same, but you can really see already the big difference when you look at scandium, right? So the splitting is very visible, and it looks pretty good at low camera lens and short camera lens. But the dysprosium improvement is really quite remarkable, right? So when we took it, actually my colleague Wouter took it in the R&D, and he was just testing the stuff, and he showed it to me. I thought, wow. And one of the reasons I told wow was because, looking at the published or available in all kinds of literature EELS data, we could not find something as good as this dysprosium H. And then we thought, why don't we go to our neighbors, synchrotron colleagues, and we opened some X-ray absorption data, and we saw that basically what we see really matches the X-ray absorption data, which actually rings the bell telling us that we cannot really get any better results here. So, we were actually running also some real samples with it, not only DSO, with our collaborators at IMAT, and they were looking also at some films grown on top of each other, and they were wondering about chemistry. And they were doing quadruple eels, so 4 energy ranges, so that's the simulation. And here is the practical real data. And it all looks very good. What I think is remarkably good is the fact that you can actually see the split here at europium M4H, which is at quite high onset. And we showed it to the people who grew the film, and they actually saw some deep physics and chemistry in it, right? I do not go there commenting on it. You really need to know the material. But I think it's really nice that you can answer some scientific questions with it. Here again, let's go back to DSO. But the parameters are a bit different to the triple eels I showed you before. So we are differently basically at the high HT, and the dispersion is 4 eV per pixel. So we have huge overview. Huge overview means 8 kiloelectron-volts field of view. So this is some kind of, let's say, entering the EDX territory when we can just look at the chemical composition. And we can also do multi-eels. In this case, we went for triple eels. This is so-called low loss. That's low loss. It contains the ZLP, but it extends almost to 8 keV. And then dysprosium, at the next energy window, looks really good. And this, I think, is really crazy cool that we can see dysprosium L edges with eels on the onset of like 8 keV to 9 keV. And this all actually inspired us to think, okay, can we also enter the X-ray absorption territory? Can we actually maybe play with stuff which the synchrotron people are doing? And this was also inspired by actually a sample we were looking at, we were looking at some glasses with crazy compositions and a lot of precipitates in it. And they were wondering if all the precipitates are the same or not. But the guys also had some measurements from synchrotron, but they were averaged because, they didn't have simply the spatial resolution. And we started playing with it and thinking, can we do same with eels? And usually the challenges of doing this kind of stuff with eels are related actually to the huge chromatic aberration when you are looking at this high HTs and loss in energy resolution, basically. I will not go back deep into the optics, but actually with Iliad, a lot of nasty things are fixed thanks to the integration. And here is a nice example which Sorin, my colleague, took using, let's say, another producer filter mounted on Spectra Ultra here, and copper edge also taken with Iliad eels. You can first of all see that the onset is where it needs to be, but also the fine structure is really cool, right? You can see all these nice elements which tell you a lot about fine chemistry and fine physics of the materials. So actually Sorin was quite a lot presenting the stuff at the conferences this year, so I will not go deep into details, but in short, we teamed up with Claudia Schnorr. She's a professor at Leipzig University, and she is really a synchrotron person. It was very cool, very fun collaboration. And she advised us a lot of stuff, how the synchrotron people act, what they do. And among the advices was the fact that they use copper like we use the cross-grating in microscopy. And basically, that's why we did quite heavy testing with copper sample, just to try benchmarking, and it actually performed very well. We could get the bone lengths out of it. And this is also a fun example because you can see the onset is really high, and I know that the guys are going further and further. As I told, we don't have that much time, and Sorin was presenting it quite actively. And basically, a couple of weeks ago, we submitted a paper. The details are very well described here. All the data from eels, which I was showing so far, are taken with our own detector. We called it Zebra because it has very elegant design, right? It has stripes, 5 CCD stripes, which are one-dimensional. So there is 1 pixel and 2K pixels. And there are 5 stripes, and every pixel is also elongated because it's basically optimized for eels, and you need to look at the edges. It's pretty fast, right? It can run up to 10K spectra per second at nearly 100% duty cycle. And I several times already shown the multi-eels, so we can go up to 5 energy ranges. In short, how it works, while you are illuminating one strip, you are reading out the previous one, and you run like this pretty well, right? You can also do one region with it, nothing prevents you from doing it. And this is a nice example. I think it was actually a semi-material. Dan, he used to work at TEM. Now we actually hired him. He is our colleague at ThermoFisher. And he was looking at this semi-sample, which has quite rich chemistry. And what I like here is that basically the sample contained both silicon and silicon oxide. And he recorded both silicon L and silicon K. And you can see they are both nicely sharp. If you used to do eels, you usually know that you have to choose which edge you have to keep sharp. So this is something pretty cool, and this is something really relying on always in focus technology combined with multi-eels. Couple more words on the cameras, right? As I told, all the stuff I showed before was taken with Zebra. But if you want to enable some specific use case, we have the System Connect package, which enables you to use some other cameras. And at our installation, actually in Antwerp, with the team of Joverbeck, we collaborated on heavily testing the QD Merlin for various use cases. I mean, I just placed here some examples, some for this TEM, filtered, non-filtered, also, of course, some atomic eels, and it works pretty well. I will not stop stop here for much. There is also low loss and so on. But I'm now going to jump to actually software, because software is super important for the ease of use. And in Iliad, EELS is implemented into Velox with a lot of nice goodies. Yes, I don't have much time, so I will rush through the final. I mean, we can do atomic mapping. You probably could expect this. Some examples are here. And we can also have the field-free imaging capabilities. So we have the corrected Lorentz TEM module, basically when we switch off the objective lens, and we can still get into pretty good spatial resolution. Here, again, I will not talk much. This is a collaboration we are doing with Shelley Conroy from Imperial. And this is her samples. Basically, they are multiferroic films, really pretty stuff. And we're doing the webinar with her. I will host. She will speak because it's really her research. She deeply knows the material. On the 11th of December, it's free. It's on the Royal Microscopy Society. Here is the link if you want to register. And of course, I love spectroscopy, so we did also field-free eels for one of my favorite samples. This bunch of perovskites on top of each other. And there is no problem on doing the chemical analysis in it in field-free. That's really very fresh. We just started playing with this, taken a couple weeks ago. I'm coming to the end. So this is our product portfolio. I did not speak about Talos, but I showed some example from Spectra. We very recently launched Iliad, and we are talking about Iliad a lot now. And what's new with Iliad is basically the expansion of sample integrity with introduction of the nanopulsar, pushing the horizons of eels with Iliad eels, and deep hardware software integration of all the things into one platform. And here in the end, I would really love to thank my colleagues. You know, just a fun fact, coming summer, we're celebrating 20 years birthday of Titan. I think Titan was a breakthrough, and there was a lot of amazing science, also quantum research, which the guys did with Titan. And quite a few names here on the list. The guys were really instrumental for Titan introduction. And I feel really proud just to be a part of this gang and now to introduce Iliad this year. And we are really, of course, looking forward to see all the amazing research which will now come out of the new platform, the Iliad. Thanks for your attention.
All right, thank you very much. We have time for one question. Anybody got a question about really cool eels?
You can also ask me questions in the corridor.
All right. In that case, I think we'll move along to the next talk. Thank you again.